Yeah, I hope you can see my screen now. Good morning and good afternoon, everyone. My name is Qian, and I'm now a PhD student in TU Delft. So I'm very happy to be here and share with you about our ongoing research. And together with my colleague Sebastiaan, who is also in this workshop, we joined these acoustic groups from TU Delft and start this kind of nice project from last year, so 2021. The aim of our project is to use like multispectral, multi-beam backscatter data to do seafloor characterization. And we also put the focus on mapping the existence of marine benthos, such as like marine species living in or on the surface of the seafloor, such as shell aggregations. And this kind of knowledge of the marine habitats and also distribution of the species are very important for the assessment of habitat information, biodiversity. And of course, it let us know like which area we should protect and its further management. And also it's very relevant to the planning of humans' offshore activities. So with this kind of objective, we selected 2 areas in the North Sea and did measurements in last summer, so in July and August separately. And as you can see, the areas are located in the north of the Netherlands in the North Sea. And we selected these areas also based on some previous biological research. So for example, this area 80, which surveyed in July, we were expected it will like contain some buried shells in the sediment. And for the area Bakumsastena, so we'll call it like BOS. And this area we expect it will like, there will be like more oyster reefs, and also the sediment can be harder, for example, containing some stones and boulders. During the measurement, we also use like multiple systems. So we use a multispectral system like ultrasonic 2026 and operating it with 4 frequencies, 90, 200, 300, and 450. And a single frequency multi-beam system from Kongsberg EM2040C and operating at 300 kilohertz. And also we've used a single beam system and collecting data at 24 kilohertz. But actually, for now, we are mainly focusing on the processing of the data from the first system, so from the multispectral multi-beam system. But we've also checked the consistency between the bathymetry and backscatter mosaics from like 300 kilohertz from the first 2 systems. So in this figure, you can also actually see the bathymetry map of our measured areas. And we've also included the 26 box core sampling locations like on this plot. And as you can see, actually, this area is very sandy area. So basically from the medium grain size doesn't really vary too much. So basically from fine sand to medium sand. And especially for the area 80, which surveyed in July, it's mainly like fine sand. And the western side of area BOS basically is a continuation of area 80. And it has some like variation in medium grain size on the eastern side, but still like not very large. And here we also present a more detailed like analysis of the sediment composition. So including the volume percentages of mud, sand, gravel, stone, dead shell, and bivalves, which is like the living bivalves. And you can, from the percentage of sand, you can also see the high volume percentage of sand in this area. And there are also some variation like within gravel, but not much like in dead shell and bivalve. And unfortunately, we actually didn't really find many existence of buried shells or oyster reefs in our measured area, which is really a pity. But we tried to find But we try to find existence of a species called the lanitia, which is actually the sand mason worm. So it actually builds tubes that consists of sand and shell fragments that can somehow protruding from the seafloor. And also the mollusks, basically also the species with hard shells. So this kind of animals may affect the backscattering process, like near the seafloor, because of their special shapes or hard shells, as you can imagine. And by density here, we actually mean the number of individuals in like per square meter, like on the seafloor. And on the right, you can also see like a more visualized results of the sample space. So we actually did a PCA like on all these sample properties of 26 sampling locations. And with this PC1 and the first and second PC as the two axis spans, you can actually see how these sample properties are distributed. And also these blue arrows here are indicate the contribution of different property vectors. And of course, there are some normalization here. So the length of them didn't really represent a real range. And also the dots in this figure indicate like all the sampling locations. So on this kind of biplot, you can see the first PC. So the primary information of the sample space is basically from the percentage of gravel and also dead shell sand, and also the density of the sand mason worm. And also on this plot, the samples like that are close to each other having like more similar properties. And we can see some exceptions that have very high percentage of mud or percentage of gravel, which are kind of out of the aggregation. So with this kind of visualization, we also want to relate our acoustic analysis results with these sample analysis results. So regarding our backscatter research, so we currently only did a relative correction by accounting for the effect of transmission loss, sonar settings, and beam footprint size. So it's not really absolute calibration, but as you can see from this backscatter strength plot, like along the like across the track, there is actually a nice alignment like between these track lines and actually for each frequency. So we are still like trusting this data and do seafloor characterization, like using this kind of relative backscatter data. Yeah, and based on this corrected backscatter data, we further applied two classification methods and then relate the acoustic classes with the sample property analysis you just saw before. So the first method is called base classification, which was actually developed by Professor Simons and Snellen in our group like years ago. And this method is basically based on the assumption that backscatter strength from one specific frequency and incident angle can be modeled as like a random variable. And because it is like from each beam, the backscatter strength we use is the result of averaging over a lot of scattered pixels, so signal footprint. So it can be modeled as a combination of several Gaussian distributions. Like shown in this figure. So we have 4 classes here. And yeah, here you can also see the comparison between the measured and fitted histogram. And based on this intersection of these 4 fitted single Gaussians, we can determine the decision boundary of different classes. But because like the beam angles actually near the nadir, they actually have not that much scatter pixels, so it might violate the central limit theorem and cannot be modeled as like a Gaussian, Gaussian distributions. So we actually choose some reference beam angles with many scatter pixels and to ensure the robustness of this fitting. And apply this kind of percentage distribution of different base classes also to like all the other beam angles. So as you can see, this is a nice way to deal with this relative backscatter, but it actually only considers information from like the individual beam angles. So it neglects some information like from other angular ranges. So we simply did another classification method, which is basically choose 3 mean backscatter values from 3 angular ranges, like you see here. So basically 0 to 25 degrees, 25 to 55 degrees, and 55 to 65 degrees, and plot their mean backscatter values here, and finally do a hierarchical clustering like per frequency to compare with the base classification method. And I present the frequency of 90 and 300 kilohertz here only. So actually, so here is the example of area boss, and actually for different frequencies, we can see from different areas, there is a different kind of variation with these angular ranges. And also for different angular ranges, some different like areas are highlighted in the highest backscatter values. And based on these 2 methods, I also need to mention like because this is like unsupervised classification, so we select the number of classes, for example, in base class based on the goodness of fitting of these Gaussian distributions, and then based on that, we further select the optimal number of classes in the hierarchical clustering. So, and next I will show you some like maps of the classification results from both 90 and 300 kilohertz. And actually you can see, so in general, I will say the classification results from both methods, base and hierarchical clusters, doesn't really like change too much. And also one thing to mention here is about the results for 90 kilohertz in area 80. So you can see there is a lot of scattered noise classes here, which might be caused by the rough weather conditions during surveying, because we met really large waves during night. This mostly affect the data, backscatter data, like at 90 kilohertz. So you can also see it in like the classification results. But except for that, actually for area 80, it doesn't show many difference like between frequencies and between methods. But for area boss, actually some distinct patterns, like the highest frequencies, like the highest clusters, like in the hierarchical clustering, actually reveal some different patterns, spatial patterns than base classification, so shown in the red area here. But you can see also these classification results also kind of affected by the noise in the nadir part, so there is some striped effect here. And also because we extract like 3 features from the whole like half swath of the angular response curve, so it sacrifices the spatial resolution a bit compared to the base classification. And then we get back to the biplots I showed you before. So here's when I overlay the color of different classification results on those biplots. So in general, for both classification methods, if you look like along the first axis of this, like the first principal components, like in the sample space, the from low to high acoustic class is actually also follows the change of the like the first principal component. So it basically also can represent the sample space from some extent. And of course, the highest class often occurs with like the highest number, the highest percentage of grayball, and also actually the highest existence of like, for example, the sand mason worm density, and also the volume percentage of living bivalves. When comparing like both classification methods, actually the hierarchical clusters here further can distinguish the contribution of the percentage of grayball and also the species density here, which is and also along like the axis of the percentage of bivalves and also sand mason worm density. They basically, these samples are classified as like one class, which is like a nice thing to relate to the sample space here. So we have like a nice first attempt to relate the acoustic classification results with these sample analysis results, but there's still like a far way to go, like to really do like the predictive modeling to predict the distribution of marine benthos on the seabed. So the first reason is we have less samples. For now, we have only 26 box sampling locations. And because the box for sampling is quite expensive, so maybe in the future we can also consider something like the video transects. And also for now, as you can see, we didn't really explore the full use of the multispectral data. We are doing it like in a single frequency way, but we are hesitating to combine these multispectral features because first we want to make sure that they are sensing the same parts of seafloor. So we want to also determine the penetration depths of different like acoustic signals in different frequencies. We have tried to do something with that relating to the depth uncertainties in the bathymetry data. Some of you maybe know we have like a working package called AMUST to determine the depth uncertainties. But for now, we find that there's some misalignment with between ultrasonic data and the model itself. So yeah, this is still the ongoing research like in this project. Regarding some other questions for this working group, for this workshop, so like the research areas that we think that maybe we need more attention. So first is still about the calibration, but this might be already addressed by too many people. But we still found that, like for example, the ultrasonic data and its 450 kilohertz really have some steep like strain behavior in these angle response curves. And because it's kind of systematic thing, so we don't think it's because of the seafloor, so might be attributed to the calibration of sonars. So this is still like an research area that requires attention. And the second one is we have met problems with rough weather conditions and the noise it brought to our Backscatter data. So we are wondering if possible, there will be people like developing such kind of tools in the future to reduce such kind of noise caused by rough weather conditions. And also the last point is the development of backscatter models to relate it to the sediment properties. So for now we have APL of working for frequencies up to 100 kilohertz, but it's not really can be like confirmed on the usage of higher frequencies. So if there will be like more development of this kind of model for higher frequencies, for example, 3 and 450 kilohertz, that would be also very nice. Yeah, so I think this is actually the last point I want to share. And yeah, many thanks for your listening. And if there are any questions.
Yeah, questions?
What was the algorithm you used for hierarchical clustering?
Clustering. Actually, I just use like a function built in the MATLAB. So, and specifically, I use the complete linkage and also like the Euclidean distance. So I think it's not a very, uncommon setting.